Hello viewers, welcome to online course on Mathematics 3. This course basically for undergraduate student or BTech student of engineering field. Today we are going to discuss about the legendary equation and the legendary function of series solution of ordinary differential equation. Myself Sanjay Vishwas, Assistant Professor of Mathematics, Department of Applied Science and Humanities of Guru Nanak Institute of Technology. Here is my details of contact information. If you have facing any kind of problem regarding my online class, you can call me or send message through my mail ID. Before we start today's lecture, let's quickly recall in the last lecture. So in the last lecture we have discussed about the Bessel's equation and the Bessel's function of module 4, that means a partial differential equation and the series solution of ordinary differential equation. So in this lecture we have discussed about the definition of the Bessel's equation, and after that we have talked about the some solutions of Bessel's differential equations, and after that we have talked about the series solution of Bessel's equation, and then we have discussed about the recurrence relation and Bessel's functions as well. Okay, and some related examples we have discussed in the previous class. So today we are going to discuss about the legendary equation and the legendary function of series solution of ordinary differential equation. Okay, and this is my sixth lecture on module 4, that means the partial differential equation and the series solution of ordinary differential equation. So here is the content of today's lecture. At first we will talk about the definition of the legendary equation, and after that we will discuss about the solutions of the legendary differential equation, and the general function of legendary equation we will discuss in this lecture. And after that we will study on the orthogonal properties of the legendary polynomials for ordinary differential equations, and then we will talk about the recurrence formula of legendary functions, and after that we will discuss some related examples on legendary equation and legendary function of ordinary differential equations. At first we will begin with the definition of the legendary equation. So what is the legendary equation? So a differential equation of the form 1 minus x square into d2y dx2 minus 2x into dy dx plus n into n plus 1 of y is equal to 0 is called the legendary equation where n is a positive integer, and we can write it equation number 1. Or this equation can also be written as ddx of, so the first two terms can be written as this, that means ddx of 1 minus x square into dy dx plus n into n plus 1 of y is equal to 0, and we can write it equation number 2. So this equation, that means equation number 1 or equation number 2, is called the legendary equation where n be any positive integer. Now we will move on the solution of legendary equation. So here is the solution. Let the series solution of equation 1, that means the legendary equation, be y is equal to summation over r is equal to 0 to infinity ar into x to the power k minus r, where a0 is not equals to 0, and we can write it equation number 3. This is the solution of the legendary equation. Okay, so we consider this one. So now the first order derivative of this solution, and it is equals to dy dx. Okay, and dy dx is equal to summation over r is equal to 0 to infinity ar into derivative of x to the power k minus r, and it will be k minus r into x to the power k minus r minus 1. And the second order differentiation of equation 3, and it will be summation over r is equal to 0 to infinity ar into k minus r into k minus r minus 1. So the second order differentiation, it will be this one. Okay, into x to the power k minus r minus 2. So the series solution of the legendary equation, and we consider this one, that means y is equal to summation over r is equal to 0 to infinity ar into x to the power k minus r, okay, where a0 is not equal to 0, and its first order derivative, it will be summation over r is equal to 0 to infinity r into k minus r into x to the power k minus r minus 1, and this one is the second order differentiation of the series solution of equation 1, that means the legendary equation. So now substituting the values of y dy dx and d2y dx2 into equation 1, that means in legendary equation we have 1 minus x square into second order differentiation, that means summation over r is equal to 0 to infinity r into k minus r into k minus r minus 1 into x to the power k minus r minus 2, okay, minus 2x into, this is the second term of the legendary equation, and it will be 2x into dy dx, okay, and dy dx is equal to summation over r is equal to 0 to infinity r into k minus r into x to the power k minus r minus 1 plus third term, and third term it will be n into n plus 1 into y, that means summation over r is equal to 0 to infinity r into x to the power k minus r, and this is equals to 0, okay. So after substituting the value of y dy dx and d2y dx2, we will get this one. So now simplifying this equation, and from this we will get summation over r is equal to 0 to infinity, okay, after multiplied by 1 it will be r into k minus r into k minus r minus 1 into x to the power k minus r minus 2 plus, and after multiplied by x square we will get summation over r is equal to 0 to infinity r into n minus k plus r into n plus k minus r plus 1 into x to the power k minus r is equal to 0. So after simplifying this equation, we will get this one, okay, and we can write it equation number 4. So now equation 4 is an identity. So to get the integral equation, we equate to 0 the coefficient of the highest power of x, namely x to the power k, in equation 4 and obtain, okay, when we put r is equal to 0. Then from the second term we will get a0 into n minus k into n plus k plus 1 is equal to 0. This is the coefficient of x to the power k in the second term, and from this equation we will get the value of k, where a0 is not equal to 0, and the value of k are n and minus of n plus 1. So the roots of the initial equation are unequal and differ by an integer, okay. So the roots are n and minus of n plus 1. So now equating to 0 the coefficient of x to the power k minus r, okay, x to the power k minus r in equation 4, and we get from this equation 4 we get a r minus 2 into k minus r plus 2 into k minus r plus 1 plus ar into n minus k plus r into n minus k minus r plus 1. So from the first term we will get this one. If we put r minus 2 is equal to r, we get the first term, that means this one, okay. So a r minus 2 into k minus r plus 2 into k minus r plus 1, and from the second term we will get the coefficient of x to the power k minus r, it will be ar into n minus k plus r into n minus k minus r plus 1 is equal to 0. So from this equation we will get the value of ar, and ar is equal to minus of k minus r plus 2 into k minus r plus 1 by n minus k plus r into n minus k minus r plus 1 into a r minus 2. And this is the recurrence relation of the given legendary equation, okay. And lastly, equating to 0 the coefficient of x to the power k minus 1, and from equation 4 we get a1 into n minus k plus 1 into n plus k is equal to 0. This is the coefficient of x to the power k minus 1. and from this we'll get a1 is equal to 0 for both k is equal to n and minus of n plus 1. So in that case, while the coefficient a1 is equal to 0. Okay, so now putting r is equal to 3, 5, 7 in equation 5. This is the recurrence relation of the given legendary equation, So if we put in r is equal to 3, r is equal to 5, r is equal to 7 and so on in equation 5, we noting that a1 is equal to 0, we have a3 is equal to 0. So a3 is equal to this one into a1. So where a1 is equal to 0, so the right hand side is equals to 0. As well as a5 is equal to 0, a7 is equal to 0, a9 is equal to 0. That means the odd coefficient of a, that means a1, a3, a5, a7, a11, a9, okay, a13 are all 0. And so we can write it equation number 6, and which hold good for both k is equal to n and minus of n plus 1. Now we are going to find the coefficient a2, a4, a6. Okay, that is the even coefficient of a, and we consider the two cases here. So case number 1, when k is equal to n, then from equation 5 we'll get ar is equal to minus of n minus r plus 2 into n minus r plus 1 by r into 2n minus r plus 1 into a r minus 2. Okay, when we take k is equal to n, we'll get this one, and we can write it equation number 7. So therefore from equation 7, if we put r is equal to 2, 4, 6, okay, etc. Successively in equation 7, we get a2 is equal to minus n into n minus 1 by 2 into 2n minus 1 into a0. Again we put r is equal to 4, we'll get this one, that means minus n minus 2 into n minus 3 by 4 into 2n minus 3 into a2. Okay, and after putting the value of a2 in that section, we'll get minus n into n minus 1 into n minus 2 into n minus 3 by 2 into 4 into 2n minus 1 into 2n minus 3 into a0. So rewriting equation number 3, so we have for k is equal to n. Okay, so this is the general solution, or the, and this is the general solution of the given legendary equation. So it is actually y is equal to a0 into x to the power n plus a1 into x to the power n minus 1 plus a2 into x to the power n minus 2 and up to infinity. Okay, so now using the values of ai's, we have y is equal to a0 into, okay, the second term it will be 0, fourth term 0, that means the coefficient of a1 is 0, a3 is 0, a5 0, a7 is 0. Okay, but the coefficient a0, a2, or a6, a4 are all exist. Okay, and they are this one, and they are a2 is equal to this, a4 is equal to this, and so on. So using the values of ai's, we have y is equal to a0 into x to the power n minus a2 where a1 is 0. So minus a2 where a2 is equal to that minus n into n minus 1 by 2 into 2n minus 1 into x to the power n minus 2 plus a3, and a3 this is equals to 0. I have already found this one, and after that the next term it will be f4. So and f4 is equal to minus of n into n minus 1 into n minus 2 into n minus 3, okay, by 2 into 4 into 2n minus 1 into 2n minus 3 into x to the power n minus 4, and we can write it equation number 8. So which is one of the solution of the legendary equation when I put k is equal to n. And after that, when we put k is equal to minus of n plus 1, then replacing n by minus of n plus 1 in equation 8, we get y is equal to, and when we put n is equal to minus of n plus 1, okay, we will get this one, this solution. That means y is equal to a0 into x to the power minus n plus 1 minus n plus 1 into n plus 2 by 2 into 2n plus 3 into x to the power minus n minus 3 plus n plus 1 into n plus 2 into n plus 3 into n plus 4 by 2 into 4 into 2n plus 3 into 2n plus 5 into x to the power minus n minus 5 and up to infinity. and we can write it equation number 9, and which is the another solution of the legendary equation. Okay, so the legendary equation is depend on the value of k, and if k is equal to minus n, then if k is equal to n, then the legendary equation it will be y is equal to this, that is equation number 8. This is the legendary equation of uh, and equation 8, it is the legendary solution of the, and when we put, when we put n is equal to, and when we put k is equal to n, then from this equation we will get y is equal to this, and it is this equation number 8 is the solution of the legendary equation, as well as when we put k is equal to minus of n plus 1, and then from the given differential equation, that means from legendary equation we will get the solution, and this is the different from the previous solution, and it will be this one, and we can write it equation number 9, and which is the another solution of the legendary equation. That means the solution of the legendary equation is dependent on the value of k. Okay, and that means the solution of the legendary equation are depend on value of k. Let us move on the next slide. So in this slide we will discuss about the legendary function or legendary polynomial of first kind and the second kind. Okay, so the solution of the legendary equation is called the legendary function of the legendary polynomial. Okay, so when n is a positive integer and a0 is equal to, so we consider this one, a0 is equal to 1 into 3 into 5 and up to 2n minus 1 by n factorial. Then the solution 8 of the legendary equation 1 is denoted by Pn of x. Okay, and Pn of x is called the legendary formula for the first kind or legendary polynomial of degree n, and it can be written as Pn of x is equal to 1 into 3 into 5 and up to 2n minus 1 by n factorial into x to the power n minus n into n minus 1 by 2 into 2n minus 1 into x to the power n minus 2 plus n into n minus 1 into n minus 2 into n minus 3 by 2 into 4 into 2n minus 1 into 2n minus 3 into x to the power n minus 4 and up to infinity. And this series can be written as a summation, that means summation over r is equal to 0 to n by 2 minus 1 whole to the power r into 2n minus r factorial by 2 to the power r into r factorial into n minus 2r factorial into n minus r factorial into x to the power n minus 2r. Okay, so this is called the legendary formula for the first kind or legendary polynomial of degree n, where n by 2, this one is actually equals to n by 2 if n is an even number, or n minus 1 by 2 if n is an odd number. Okay, and here Pn of x is a terminating series where is in a positive integer. Again, when n is positive integer and a0 is equal to n factorial by 1 into 3 into 5, okay, and up to 2n minus 1, the solution 9 of equation 1, and it is denoted by q of n. Okay, where q of n is equal to, after putting the value of this a0 is equal to this, we will get from equation 9, and the equation 9 is the another solution of the legendary equation 1 when we put k is equal to minus of n plus 1. Okay, and it is equals to, after putting the value of a0 we will get this n factorial by 1 into 3 into 5 and up to 2n minus 1 into x to the power minus n minus 1 minus n plus 1 into n plus 2 by 2 into 2n plus 3 into x to the power minus n minus 3 plus n plus 1 into n plus 2 into n plus 3 into n plus 4 by 2 into 4 into 2n plus 3 into 2n plus 5 into x to the power minus n minus 5 and up to infinity. there are infinite number of terms, and so this is also the legendary function or the polynomial function of degree n. But Qn of x is an infinite or non-terminating series, as n is a positive integer, where p of n is a terminating series, where n as a positive integer. So therefore, the general solution of the legendary equation, and it will be y is equal to a into pn of x plus b into qn of x, where a and b are the arbitrary constant, and pn of x and qn of x are the polynomial function of degree n, or the legendary function of degree n, or first kind and the second kind. And after that we are going to the next part of the legendary function, and this is actually the genetic function or legendary polynomials. Okay, so there is a theorem on genetic function for legendary polynomial. Pn of x is the coefficient of h to the power n in the expansion of 1 minus 2xh plus h square whole to the power minus half in ascending power of h, where modulus of x is less or equal to 1, modulus of h is less than 1. So here is the proof of the theorem. Since modulus of x is less or equal to 1 and modulus of h is less than 1, so these two conditions are given in the above theorem. We have 1 minus 2xh plus h square whole to the power minus half, and it can be written as 1 minus h into 2x minus h. We take h as common from the last two terms, we get this one. Okay, 1 minus h into 2x minus h whole to the power minus half. Now applying the binomial expansion of this function, we will get 1 plus h by 2 into 2x minus h, this is the second term, plus 1 into 3 by 2 into 4 into h square into 2x minus h whole to the power 2. Okay, so up to the n minus 1n term, that means 1 into 3 and up to 2n minus 3 by 2 into 4 and up to 2n minus 2 into h to the power n minus 1 into 2x minus h whole to the power n minus 1. This is the nth term of this binomial series, plus 1 into 3 and up to 2n minus 1 by 2 into 4 and up to 2n into h to the power n into 2x minus h whole to the power n and up to infinity. So there are infinite number of terms. So this term is the nth term and this one is the n plus 1th term of the given series. So therefore the coefficient of h to the power n from the above series, we will get the coefficient of h to the power n, and it will be 1 into 3 and up to 2n minus 1 by 2 into 4 and up to 2n into 2x whole to the power n. Okay, plus 1 into 3 and up to 2n minus 3 by 2 into 4 and up to 2n minus 2 into n minus 1 c1 into minus 1 into 2x whole to the power n minus 2. Okay, if we expanding this term, that means 2x minus h whole to the power n minus 1, as well as this term, that is 2x minus h whole to the power n, we will get this one. Okay, this is actually the coefficient of h to the power n, plus 1 into 3 and up to 2n minus 5 by 2 into 4 up to 2n minus 4 into n minus 2 c2 into minus 1 whole to the power 2 into 2x whole to the power n minus 4 and up to infinity, and we can write it equation number 1. This is actually the coefficient of h to the power n, and from this series we will take 1 into 3 into and up to 2n minus 1 by 2 into 4 and up to 2n as common, and after that we will get x to the power n minus 2n into 2n minus 1 into n minus 1 into x to the power n minus 2 by 2 to the power 2. Okay, and this term, that means 1 into 3 and up to 2n minus 1 by 2 into 4 up to 2n as a common, plus 2n into 2n plus minus 1 by 2n minus 1 into 2n minus 3 into n minus 2 into n minus 3 by 2 factorial into x to the power n minus 4 by 2 to the power 4 and up to infinity. After simplifying this series, we will get 1 into 3 and up to 2n minus 1 by 2 into 4 up to 2n, and we'll get this one. Okay, that means x to the power n minus 2n into n minus 1 by 2n minus 1 into x to the power n minus 2 plus this one is the third term. After simplifying this, we'll get this one, n into n minus 1 into n minus 2 n minus 3 by 2 into 4 into 2n minus 1 into 2n minus 3 into x to the power n minus 4. Okay, and up to infinity. And this is actually the legendary polynomial of the differential equation. Okay, so and it can be written as Pn of x. Okay, so Pn of x is the nth degree polynomial, and the Pn of x is the legendary polynomial of degree n, or legendary function of first kind. So thus we can say that summation of n is equal to 0 to infinity h to the power n into Pn of x. So where Pn of x is the coefficient of h to the power n. So summation over this is equals to 1 minus 2xh plus h square whole to the power minus 1 by 2. So 1 minus 2xh plus h square whole to the power minus 1 by 2 is called the generating function of the legendary polynomial of degree n. Okay, this is very important for solving the legendary function. So after that, we will talk about the orthogonal properties of legendary polynomials. The first property, it will be integration over minus 1 to plus 1 pmx into pnx of dx is equal to 0 if m is not equals to m. And the second property, it will be integration over minus 1 to plus 1 pnx whole square dx is equal to 2 by 2n plus 1 if n is equal to m. So here is the proof of the first properties of the legendary polynomials, or the orthogonal properties of legendary polynomials. Okay, so the legendary equation may be written as ddx of, this is the legendary equation, ddx of 1 minus x square into dy dx plus n into n plus 1 of y is equal to 0. Okay, so now we take y is equal to pm, where pn is the legendary polynomial of degree n and pm is the legendary polynomial of degree m. First of all, we will take y is equal to pn, then the legendary equation will be changed and it will be ddx of 1 minus x square into dpn dx plus n into n plus 1 into y is equal to 0. And if we put y is equal to pm in that section, we will get ddx of 1 minus x square into dpm dx plus m into m plus 1 into y is equal to 0. And we can write it equation number 2. So now multiplying of equation 1 by pm and equation 2 by pn, and then subtracting, we have pm of ddx of 1 minus x square into dpn by dx, okay, minus, so multiply by pm in equation 1 and pn in equation 2, and after subtracting we will get this one, minus pn into ddx of 1 minus x square into dpm dx plus n into n plus 1 minus m into m plus 1 into pn is equal to 0. So after simplifying this equation, and from this we will get ddx of 1 minus x square into pn dashed, so dpn dx is equal to pn dashed into pm minus, and from this we will get pm dashed into pn plus m minus n into m plus n minus 1 into pn into pm. So after simplifying this, we will get this one. Now integrating this equation between the limit minus 1 to plus 1, we have m minus n into m plus n minus 1 integration over minus 1 to plus 1 pmx into pnx dx, this is the second term of the above equation, is equal to 1 minus x square into pn dashed pm minus pm dashed pn, where upper limit is plus 1 and lower limit is minus 1. Okay, so if we put x is equal to plus 1, we'll get this term is 0, as well as when we put x is equal to minus 1, we'll get this one 0. So therefore integration over minus 1 to plus 1 pmx into pnx dx is equal to 0 if m is not equals to n. So hence the proof of the first properties of legendary polynomial. And after that we will discuss about the second properties of orthogonal properties of legendary polynomial. So we have 1 minus 2xh plus h square whole to the power minus half is equal to summation over n is equal to 0 to infinity h to the power n into pn of x. So this is the generating function of the legendary polynomial I have already discussed in the previous slide. Okay, so now squaring both sides, we have 1 minus 2x h plus h square whole to the power minus half. After squaring, we will get this one is equal to summation over n is equal to 0 to infinity h to the power 2n into pn of x whole to the power 2 plus 2 into summation over m is equal to n is equal to 0 to infinity, where m not equals to n, h to the power m plus n. Okay, so if after squaring the right hand side of this equation, we will get this one. The first term it will be this, second term it will be 2 into summation over m is equal to n is equal to 0 to infinity, m is not equals to n. Okay, in that case where m is not equals to n, h to the power m plus n into pmx into pn of x. And now integrating on both sides, between the limit minus 1 to plus 1, we have summation over n is equal to 0 to infinity minus 1 to plus 1 h to the power 2n pnx whole square into dx plus 2 into summation over m is equal to n is equal to 0 to infinity minus 1 to plus 1 h to the power m plus n into pmx into pnx dx, and this is equals to integration over minus 1 to plus 1 dx by 1 minus 2xh plus h square. Okay, this is the left side of the above equation. So you know the second term of this integration, and it will be 0. Why it is 0? So for m is not equals to n, the integration over minus infinity to plus infinity pmx into pnx is equal to 0. This is the first properties of the legendary polynomials, you know that. So from this integration we will get summation over n is equal to 0 to infinity minus 1 to plus 1 integration over h to the power 2n into pnx whole square into dx, and this is equals to integration over minus 1 to plus 1 dx by 1 minus 2xh plus h square. So you know the second integration of the left hand side is 0 as m not equals to n. So from this we will get minus 1 by 2h. This is the integration of the right hand side of the above equation. Okay, so this is equals to 1 by 2h into log of 1 minus 2xh plus h square, but the upper limit is plus 1 and the lower limit is minus 1, you know that. So after putting the value of upper limit as well as lower limit, we will get from this 1 by 2h into log of 1 plus h whole square by 1 minus h whole square. After simplifying the log function, we will get 1 by h into log of 1 plus h by 1 minus h, and this is equals to 2 by h into, you know that log of 1 plus h by 1 minus h, it is equals to log of 1 plus h minus log of 1 minus h. And after expanding the log function as a series, we will get this one. So 2 by h into h plus h cube by 3 plus h to the power 5 by 5 and up to infinity. And we can write this series as a compact form, that means summation over n is equal to 0 to infinity 2 into h to the power 2n by 2n plus 1. Okay, so now equating the coefficient of h to the power 2n on both, we will get integration over minus 1 to plus 1. Okay, this one actually pn of x whole square into dx, and this is equals to 2 by 2n plus 1. Hence the proof of the orthogonal property, that means the second orthogonal properties of legendary polynomial. After that, we will discuss some recurrence formula of legendary polynomial. So here is the formula: 2n plus 1 into x pn is equal to n plus 1 pn plus 1 plus n into pn minus 1. This is the first recurrence formula of legendary polynomial. So here is the proof of the recurrence formula. So we have 1 minus 2hx plus h square whole to the power minus half, and it is equals to summation over n is equal to 0 to infinity h to the power into pn of x. Okay, this is the generating function of the legendary polynomial, you know that. So now differentiating both sides of with respect to h of the above generating function of legendary polynomial, we have minus half into 1 minus 2hx plus h square whole to the power minus 3 by 2 into minus 2x plus 2h. After differentiating it with respect to h, we will get this one. And the right hand side, it will be summation over n is equal to 0 to infinity n into h to the power n minus 1 into pn of x. Okay, so now simplifying this equation, we will get x minus h into 1 minus 2hx plus h to the power 2 whole to the power minus half, and it is equals to, so now 1 minus 2hx plus h square to the power minus 3 by 2 can be divided into two parts. Okay, so this one, that means 1 minus 2xh plus h square to the power minus half by 1 minus 2hx plus h square. Okay, so after multiply by 1 minus 2hx plus h square, you will get this one. And the right hand side, it will be 1 minus 2hxx plus h square into summation over n is equal to 0 to infinity n into h to the power n minus 1 into pn of x. Okay, so after simplifying this equation, we will get x minus h into summation over n is equal to 0 to infinity h to the power n into pn of x, and it is equals to 1 minus, and you know this is actually the generating function of the legendary polynomial, and it is equals to, you know, summation over n is equal to 0 to infinity h to the power n into pn of x. Okay, and this is equals to this 1 minus 2hx plus h square into summation over n is equal to 0 to infinity n h to the power n minus 1 into pn of x. So now equating the coefficient of h to the power n from the both side, and we have, so from the left side we will get x into pn of x, this is the coefficient of h to the power n as well, minus pn minus 1 of x is, it is equals to n plus 1 into pn plus 1. Okay, so if we put n minus 1 is equal to n, we will get this one. This is the coefficient of h to the power n after putting n minus 1 is equal to n, and minus 2xn into pn of x plus n minus 1 into pn minus 1 of x. These are the coefficient of h to the power n, and after simplifying this equation, we will get the recurrence formula. 2n plus 1 into x pn is equal to n plus 1 into pn plus 1 plus n into pn minus 1. Hence the proof of the recurrence formula of legendary polynomial. So after that, we will take one more recurrence formula for legendary polynomial, and it will be n into pn is equal to x pn dashed minus pn minus 1 dashed. Okay, this is another formula for legendary polynomial. So here is the proof of the given recurrence formula. So we have, you know, this is the generating function of the legendary polynomial, 1 minus 2hx plus h square whole to the power minus half. Okay, and it is equals to, you know, that summation over n is equal to 0 to infinity h to the power n into pn of x. Okay, and we can write it equation number 1. So now differentiating this equation with respect to h, and we have minus 1 by 2 into 1 minus 2hx plus h square whole to the power minus 3 by 2 into derivative of h, so that means 2x. So derivative of h, it is 0, first term is 0, second term it will be 2x, and third term it will be 2h. Okay, that is minus 2x plus 2h. That is equals to summation over n is equal to 0 to infinity n into h to the power n minus 1 into pn of x. and we can write it equation number 2. So again, differentiating equation 1 with respect to x, and we get h into, so after differentiating this equation with respect to x, we get h into 1 minus 2hx plus h square whole to the power minus 3 by 2 is equal to summation over n is equal to 0 to infinity h to the power n into pn dash x. Okay, in that case the right hand side it will be pn dash x into h to the power n. Okay, now multiple by x minus h on both sides will get this one. That means h into x minus h into 1 minus 2hx plus h square or to the power minus 3 by 2. It is equals to x minus h into summation over n is equal to 0 to infinity h to the power n into pn dash x. And we can write it equation number 3. So from equation 2 and equation 3 we have h into summation over n is equal to 0 to infinity. Okay, n into h to the power n minus 1 into pn of x. So this one is equal to x minus h into summation over n is equal to 0 to infinity h to the power n into pn dash x. Okay, so now equating the coefficient of h to the power n on both sides, we will get n into pn of x, okay, is equal to x into pn dash x minus p n minus 1 dash x. This is the coefficient of h to the power n. And from this equation we get n into pn is equal to x into pn dash minus pn minus 1 dash. Hence the proof of the second recurrence formula of legendary polynomial. So similarly we will find the some more recurrence formula of legendary polynomials, and they are 2n plus 1 into pn is equal to pn plus 1 dash minus pn minus 1 dash, and n plus 1 into pn is equal to pn plus 1 dash minus x into pn dash. Okay, and then the Rodriguez formula of the legendary polynomials, it will be pnx is equal to 1 by n factorial into 2 to the power n, the nth order derivative, that means dn dxn into x square minus 1 whole to the power n. This is called the Rodriguez formula for the legendary polynomials. So after that we will discuss some related examples on legendary polynomials. So here is the example. Express p of x is equal to x to the power 4 plus 2x to the power 3 plus 2x square minus x minus 3 in terms of legendary polynomials. So here is the proof of the legendary polynomials. So we have p0 of x. So these terms are all given. Okay, so p0 of x is equal to 1, p1 x is equal to x, p2 of x is equal to 1 by 2 into x square minus 1. Okay, so we have find this terms from the Rodriguez formula, or the generating function of the legendary polynomials. Okay, or p3 of x is equal to 1 by 2 into 5x3 minus 3x, and p4 of x is equal to 1 by 8 into 35x to the power 4 minus 30x square plus 3. And from the last equation, that is from p4 of x, we'll get the value of x to the power 4, and it will be 8 by 35 p4 of x plus 6 by 7 x square minus 3 by 35. Now from the third equation, that means p3 of x, will get the value of x to x3, and x3 is equal to, you know that, 2 by 5 into p3 of x plus 3 by 5 of x. And from the second equation, that means from this p2 of x, we get x square is equal to 2 by 3 into p2 of x plus 1 by 3, and x is equal to p1 of x, and 1 is equal to p0 of x. Now substituting the value of x to the power 4 from the given equation, we will get 8 by 35 p4 of x plus 6 by 7 x square minus 3 by 35 plus 2x to the power 3 plus 2x square minus x minus 3. Okay, now we put x to the power 3 in that equation, we will get 8 by 35 p4 of x plus 2 into 2 by 5 p3 of x plus 3 by 5 x. This is actually the value of x to the power 3 plus 20 by 7 x square minus x minus 108 by 35. After that we will put the value of x square, so it will be 2 by 3 into p2 of x plus 1/3. So after putting the value of x square, we will get this one. Okay, and from this equation we will get 8 by 35 p2 p4 of x plus 4 by 5 p3 of x plus 40 by 21 p2 of x plus 1 by 5 p1 of x minus 224 by 105 p0 of x. Okay, and this is the required expression of p of x in terms of legendary polynomials. Okay, so after that we will discuss the second example on the legendary polynomial. So that Pn of 1 is equal to 1, and the second problem, it will be Pn of minus x is equal to minus 1 whole to the power n Pn of x, and hence deduce that Pn of minus 1 is equal to minus 1 whole to the power n. So here is the solution of the given problem. Now we take the first problem. So we know that the summation of our n is equal to 0 to infinity h to the power n Pn of x is equal to this 1 minus 2hx plus h is equal to the power minus 1 by 2. So this is the recurrence relation of the legendary polynomial, you know that. So now we put x is equal to 1 in that legendary polynomials. We will get summation of our n is equal to 0 to infinity h to the power n into Pn of 1. And this is equals to 1 minus 2h plus h square whole to the power minus half. And you know 1 minus 2h plus h square, it will be 1 minus h whole to the power 2. So after simplifying this, we will get 1 minus h whole to the power minus 1. And you know that 1 minus h whole to the power minus 1 is the series function, and the series of 1 minus h whole to the power minus 1, it will be 1 plus h square and up to infinity. And this is equals to summation of our n is equal to 0 to infinity h to the power n into Pn of 1. So now equating the coefficient of h to the power n on both sides, we will get Pn of 1 is equal to 1. This is the proof of the first part of the given problem. So after that we will prove the second part of this problem. So for the solution of the second part, we first of all we will take the generating function 1 minus 2hx plus h square whole to the power minus half. It is equals to summation of n is equal to 0 to infinity h to the power n into Pn of x. Okay, and we can write it equation number 1. So now replacing h by minus h in the above equation, we get 1 plus 2hx plus h square whole to the power minus half, and it is equals to summation of n is equal to 0 to infinity minus h whole to the power n into Pn of x. Okay, so minus 1 whole to the power n of Pn of x, it is equals to, you know, minus 1 whole to the power n into h to the power n of Pn of x. We can write it equation number 2. Now replacing x by minus x in equation 1, we have 1 plus 2hx plus h square whole to the power minus half. It is equals to summation of n is equal to 0 to infinity h to the power n into Pn of minus x, and we can write it equation number 3. So from equation 2 and 3, we have summation of n is equal to 0 to infinity h to the power n into Pn of minus x, and it is equals to summation of n is equal to 0 to infinity minus 1 whole to the power n into h to the power n of Pn of x. Okay, so now equating the coefficient of h to the power n on both sides, we will get Pn of minus x is equal to minus 1 whole to the power n of Pn of x. So hence the proof of the second part of the given problem. And next we put x is equal to 1. So we have Pn of minus 1 is equal to minus 1 whole to the power n of Pn of x. You know that Pn of 1, it is equals to 1. I have already found this part of the given problem. So from this we will get Pn of minus 1 is equal to minus 1 whole to the power n. This is the proof of the third part of the given problem. So I will stop here the today's lecture. Thank you.